Hello, I wanted to take a minute to walk you through the example on page 257 of our book. And again, the book is Decision Support and Business Intelligence Systems, 9th edition. This is the Turbine textbook. This is the neural net example on page 257. Let's begin by setting up the problem. I'm going to quote from the book here. Consider a single neuron that learns the inclusive OR operation, a classic problem in symbolic logic. This is on page 256. The two input elements or variables are x1 and x2. If either or both of those variables have a positive value, the result is also positive. This can be seen on this screen. We have two variables, and if one or the other is true, then we evaluate as true. In this case, the only one of the sets that doesn't evaluate as true would be if they are both false. So they would neither one nor the other is true, it would evaluate as false. That's the problem that we have. We're given this training set. We'd like to be able then to evaluate it when we see these sets of variables in the future. How should we evaluate them? Now, this is a very simple problem of ORs, and it's a very simple example of this problem. We only have two variables. If you start to get in dozens or scores of variables, this can get to be pretty messy pretty quick, especially if they can take on more than one value, and if the rule is more complicated than just being a simple OR evaluation. You'll see that this is a table. It is very similar to what is on page 257, except for that I have added a couple of supplemental columns, namely the actual equation and the weighted sum, and I'll explain those in just a minute. I wanted to read from the bottom of page 256 very briefly. The neuron must be trained to recognize the input patterns and classify them to give the corresponding outputs. The input patterns are the combination of x1 and x2 variables, and the output pattern is variable z. That's your output. So here it says if one or the other is true, evaluate as true. Neither one is true, so it evaluates as false. You go to the next case. If one or the other is true, evaluate as true. Well, in this case, one is false, but one is true. We evaluate as true. The procedure is to present the sequence of the four input patterns to the neuron so that the weights are adjusted after each iteration. You can see this step is what an iteration is. So we iterate through, we present the two inputs, and we get an output, and we work through an equation, and it's going to learn each time it goes through the iteration. We're going to walk through the iterations in a minute. This step is repeated until the weights converge to a uniform set of values that allows the neuron to classify each of the four inputs correctly. And actually, I should say correctly or to within a given allowable tolerance. The results shown in table 6.1 were produced in Excel. That's this right here. In this simple example, a threshold function is used to evaluate the summation of input values. That's what they don't show you in their table, and it's what I do show you here, is that summation of weighted values. Here's the formula for it. We're going to go through it in just a minute. After calculating outputs, a measure of the error, that's the delta right here, between the output and desired values is used to update the weights. You'll see that the actual delta formula is the difference between the correct output and what our algorithm guesses. So in this case, it should have evaluated as 1. It did evaluate as 1. The error is 0. But in this case, we had an x1 of true and an x2 of false. So it should have evaluated as true. However, our algorithm predicts that it's going to be a 0. The difference between the 1 and the 0 is 1. The difference between the output and the desired values is used to update the weights, subsequently reinforcing the correct results. And so what we're talking about there is very simply it's going to iterate through, and every time it goes through an iteration, it's going to learn and it's going to update our weights. So what the computer wants to learn is some kind of a math function and an evaluation based on that math function, and it can set up some rules based on that. So what our math function is, well, that's our weighted sum. That's the value of a given variable multiplied by the weight of that variable, and we do that for all of our variables. That's our weighted sum. In this case, we have two zeros. Multiply those by our weights. It's the red zero times the blue weight, the green zero times the purple weight. That weighted sum is 0. And what we want to do is compare that to some threshold value and say, if I've gotten above the threshold, then I take one action. If I am below the threshold, I take another action. In this case, the threshold that I want to hit is a value of 0.5, and the action that I want to take is if my weighted sum is above 0.5, I want to assign true or yes or 1. If my weighted sum value is below 0.5, I want to assign no, false, or 0. Next, we want to discuss alpha. Alpha is very simply when we adjust our weights as we learn. How much do we adjust that weight by? And we'll explain at the end why alpha matters and why you don't just set that to be a very, very low value every time. Let's go ahead and walk through the algorithm iteration by iteration so that we can see exactly what's happening. This particular neural net algorithm begins by taking some input, and the input is our values of the variables x1 and x2. It randomly assigns them weights, although again those weights will probably be very low or very high. And or you can assign those weights also. It will run them through a weighted sum function, and so the function is a multiplier of the value of each variable multiplied by its weight. So in this case, the red is the value of variable 1 multiplied by the weight of variable 1 plus the value of variable 2 multiplied by the weight of variable 2. The weighted sum in this case, you can see, if you want to see how I calculated that, you can actually click on it and see the formula in Excel. The weighted sum in this case is 0. Our rule is if my weighted sum is greater than some threshold, then evaluate as 1. My threshold is, I have set that myself as 0.5. In this case, my weighted sum is not greater than the threshold of 0.5, so I evaluate that as 0. My error in this case then is the difference between what the actual value was in the training data compared to what the computer evaluated. In case there is no difference, and I ran that as an if statement, I said if they're the same, then the error is 0. If they're different, the error is 1. And so this time I expected a 0 and I evaluated as a 0. My error turned out to be 0, and here's what's important: I don't change my weights then. I started with a set of weights, I got no error, I have no reason to adjust those weights. So that's iteration 1. So let's do the second iteration. We take as inputs x1 and x2. We know that the output of that should be a 1 because our comparison is if x1 or x2 is true or a 1, we evaluate as 1. We feed those into our weighted sum function with the weights 0.1 and 0.3. Here's our weighted sum function. Our outcome is 0.3. Because that 0.3 is not greater than our threshold value of 0.5, we evaluate that as a 0. But when we make our comparison to calculate our error, we know that our guess is not the same as what we expected, so we have an error of 0. And in this case, now this depends on the algorithm that you want to use. Each algorithm would be different. This algorithm is going to increment the weight for variable 2, and they're going to increment it by the alpha. So you see it the weight for variable 2 goes from 0.3 to 0.5. That's because the algorithm is saying we'll increment one of the weights. It does not increment both weights at the same time. It'll only do one or the other. The specific algorithm said to increment weight 2. You'll notice that the reason that we increment the weight is because we have an error. Up here where we didn't have any error, our weights stay the same. We started with 0.1 and 0.3, we end with 0.1 and 0.3. Down here we have a 0.1 and 0.3, but because we have an error we've incremented, we end up with 0.1 and 0.5.